Hello, my name is Tanawat Unsiwilai. I'm from Robotics and Automation System Engineering. Today I'm gonna representing about the mobile robot control system by the MATLAB Simulink. So why I choose the mobile robot? Because the mobile robot is global usage in the world. It's very useful for our robotics role. And in this presentation, we have a two phase. The first phase one is about the plan description and system analysis. And the phase two, we have a controller design tuning by the PID controller. So first of all, mobile robot control, as you can see on the left hand image, it shows us the distance control by the encoder that is gonna capture the angle of the motor is rotating. And if we don't have a PID controller, we cannot know about that, and we're gonna have a space error so much. And on the right hand, you can see the example of PID controller for this 10. So this is the model of my Simulink. So the model of my controller system, we have a feedback control. It's like an encoder to capture the monitor distance. And we have a controller to be the PID controller, and the plan is a motor to control mobile robot. So, and the input is the design system, reference distance that we're gonna put it. So it's like I want to go 2 meter, I want to go 3 meter, something like that to be the input. So the output is the pen. So the pen is move, a mobile robot pen. And on the right hand too is like a PID controller, how PID controller move. The PID controller is input to be error and the controller output, because PID controller is gonna recap. It's gonna use the error and match with the input that we want, and it's gonna adjust the value to be the best value for the reference value that we want. So the plan input in the system of the control signal fed to the left and the right motor, as you can see on the picture. And this control signal are determined by the PID controller to achieve the desired heading angle. And the plan output, we have the plan outputs are the actual wheel velocity, left and right motor, and we have the encoder ticks to capture the feedback control, which are used to compute the wheel travel distance. These outputs are essential for the feedback control to maintain the desired heading. And the pen characteristic. The pen characteristic is our the dynamic. The pen attribute dynamic typical of a mobile robot, where the wheel velocity directly influences the robot heading. And non-linearity, the relation between motor input and wheel travel is non-linear due to the factor like friction or a road variation. And the delay, there might be a delay in the system anyway. So, and this slide, this page is about a preview model in MATLAB. You can see it have an encoder simulation to capture, as I said, to capture the feedback of the left and right model. And we have robot simulation on the right, and the plan is a left model and right model. And we have a PID controller to capture and to try to adjust the value to be the desired value that the reference value and input put me up. And we have a compute angle, and then this is some value on the configuration characteristic. It have a value that we can adjust the angle of the range, the cheaper rod, and the TS. It's like a sample time that we use on the PID controller to be the simulation, and we have a wheel radius, and this is the workspace configuration. So the workspace configuration is provide us the state space A, B, C, D, K is on the equation of the state space to be designed space, and we have input output delay or structure that we want, and state space for this. And you can see on the left hand it's like a formula, and my design of this project of this model is provide me on the A. It's going to be a 3 by 3 matrix right here, and the B 3 by 1 right here. The value is gonna adjust depending on the input that we give it, and we have a C, D, and K, or everything that we want to be the make a state space equation. And for system analysis 1, first of all, the frequency domain analysis is a transfer function of the system that can be derived from the dynamic of the model and the feedback control loop. On the You can see on the step response picture, and we have a board part on the right hand upper. Board part illustrates the frequency response of the system, showing how the gain and phase of the output signal vary with frequency. So is always to be the frequency and the radius capture right here. It is very useful for the continuous system, and stability margin, gain, and phase margin from the board part help assess the system robustness and disturbance right here. And you can see the Posillo map and rural cast right here for the discrete transfer function and Posillo parts to analyze the C domain. It will examine the location of hole and zero of the transfer function, which indicate system stable and response characteristic. And C transform C domain is the discrete transfer function. And the time domain analysis is have a impulse response, and we have a step response right here that I will already show you. And for the controller design, we have to double click on the PID controller, and we can tuning every value that we want. So the PID controller is a proportional, integral, and derivative. It's like a term or equation, derivative mathematical equation to adjust the value that we want. So first of all, it's a transform discrete equivalent using the method right here. And you can see on the right hand image that I put on you is a did reference distance and measure distance that we want. It shows us on the graph, and the controller output right here. So we want to adjust this value. So I already put PID tuning. I tune right here on the left hand side. I tune on the P to KP to be the 1.421, and for the KI to be the 0.25, and for the KD is around minus 0.01. And you can see it already had a rise time, setting time, all the parameter that we want to know. The overshooting around 12%. So the end of the conclusion is provide us the stable of the controlling whole stability. On the right hand, I got another tuning KPV1, KI0, and KD0. So overshooting is around 0. So it's back. And effect of the increasing PID parameter. If you increase the PID parameter, someone is gonna get down and someone is gonna increase. Right, the rise time for the KP is decrease, and overshooting increase right here. You can see right here, and I think it was really bad. And for the spread mobile design, I put the all configuration that provide to be the state space for my workspace configuration. So we have a matrix. The state space idea, the idea of state space are the matrix that uh, defining the controller state feedback from controller can be designed to place a closed loop probe in defined locations of the optimal performance. Observer design to be right here. In a discrete time and space method, take the following form right here. and for my model is use of usually model. So this is for my thinking, my presentation about mobile controller by MATLAB Simulink. So I suggest you to seeing my documentation. It has a more detail and deeply detail more than this. So is it a briefly about the presentation of the mobile robot? Thank you so much.